Hello everyone again. Let's get started with the second law of thermodynamics, part 3. So if you have followed part 1 and 2, by now you should know that we talked about two statements for the second law of thermodynamics. So the first statement was the Kelvin-Planck statement, and it was related to a heat engine. Based on the Kelvin-Planck statement, it is impossible to manufacture a heat engine which can operate on a cycle to receive heat from a single reservoir and produce a net amount of work. So it means that it is not possible to convert 100% of heat to work. This is against the second law of thermodynamics. The second statement is the Clause's statement. It's related to a heat pump or a refrigerator. It simply says that it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a low temperature body to a higher temperature body. So you cannot transfer heat from 10 degrees C to 20 degrees C just without having or leaving any other effect. So it means that you would need to provide work for transfer of heat from low temperature to high temperature to happen. So these are two statements, but they are actually equivalent. So in their consequences, and either statement can be used as the expression of the second law of thermodynamics. So because these processes are like, if you reverse a heat engine, you can get a heat pump, for instance, something like that. So they are very similar. If you look at their schematic of a heat engine and a heat pump or refrigerator, you see that only the direction of the arrows change. So these are equivalent statements. And any device that violates the Kelvin-Planck statement also violates the Clause's statement, and vice versa. Well, in the history of science and technology, there have been people who have tried to violate the first law of thermodynamics or second law of thermodynamics by constructing perpetual motion machines. So here what you see, it's a perpetual motion machine that violates the first law of thermodynamics, which is actually the energy balance. What you see on the diagram is a thermal power plant. So we know that in a thermal power plant, in the boiler, we will need to burn a fuel. Therefore, we will need to provide a QH, heat coming to the cycle. But based on this design, actually there is no need for fuel burning. Instead, the energy which is needed to actually evaporate the water and generate steam comes directly from the generator. How? So it means that the power plant will work, it will generate electricity in the generator. A portion of it will be used as electricity, and then the rest of it will actually go inside the boiler and pass through a resistance heater in order to evaporate the water there. So this is like a self-contained power plant, and as you see, there is no energy coming to this entire system. However, we do have energy going out in the form of Q out and in the form of W out. And there is no energy in, but there is energy out. So this violates the first law of thermodynamics, even if this scheme looks fine on paper, but it's not possible. So people have tried it, it does not work. There is another perpetual motion machine which violates actually the second law of thermodynamics. So this is again a power plant. In this power plant, we do have Q in, heat comes in, and we do generate work in the turbine. So far so good. However, this device tries to eliminate the Q out. So there is no Q out going to a low temperature reservoir here. Instead, the steam which is saturated now at the exit of the turbine has been suggested to be directly pumped back to the boiler. So this means that we do have a machine which actually receives energy in and converts all of this energy to work. So this is also against the second law of thermodynamics, doesn't work. So why doesn't work? Practically because of multiple reasons. You are not yet familiar with the thermodynamic cycle of this. But for now, you could imagine that the steam which is coming out of the turbine, in this case, it is nearly saturated vapor, so it's gas, and we cannot actually pump a gas in the pump in order to send it back to the boiler. So we would need to convert the saturated vapor into liquid water before we can pump it to a higher pressure. So this is not possible either. Okay, so now let's continue with reversible and irreversible processes that will help us to further understand from the second law of thermodynamics. So reversible processes, as the name suggests, a reversible process is a process that can be reversed without leaving any trace on the surroundings. So you can do the process and then reverse it without just, it's like Control Z. You do something and then press Control Z. That's simple. However, we know that this Control Z doesn't work in many cases. For instance, you know, in real world, in real life, we cannot reverse most of the things. So if you do something stupid, you cannot reverse it, right? So that's irreversible. So irreversible process is a process that is not reversible. Okay, so what does it mean? If you look at this pendulum here, if there is no friction, if the pendulum actually swings in vacuum, then it can go all the way from left to right, and this swinging process can continue forever if we do it in outer space. Then that would be a reversible process. Now, if you do this on Earth, in the atmosphere of the Earth, because of the presence of the friction, as it moves from one side to the other, gradually it decelerates, so it slows down. So this, therefore, when friction is present, the processes are irreversible. If there is no friction, the processes can be reversible, but friction makes a reversible process irreversible. Another example is in this piston cylinder. So let's say you have a gas in the cylinder, and if the process is quasi-equilibrium, meaning that very slowly you let the piston expand and then compress it very slowly in a quasi-equilibrium expansion compression process, then that can be assumed as a reversible process. But if you do it like very fast expansion and rapid, compression, so that you create a lot of turbulence, in the system, then that some of the useful energy during that turbulence will be converted to heat, then the process becomes irreversible. So anytime that you can decide whether a process is reversible or irreversible, just think whether you can reverse it without any effect on the environment, or in order to reverse it, you will need to provide some additional work in order to make that happen. So all the processes occurring in nature, and by nature we mean actually on Earth, in the atmosphere of the Earth, are irreversible. In reality, we do not have reversible process because friction is present, processes can be fast. So but this is, an idealization that we make in order to simplify the things. So why are we interested in reversible processes? One, they are easy to analyze. It's easy to analyze a reversible process because there is, for instance, it's like the background behind thermodynamics, which is assuming a quasi-equilibrium system. It makes it easy to analyze. Second, they serve as idealized models, theoretical limits to which actual processes can be compared. So they provide like a standard theoretical limit, and then we can go ahead and compare other processes. It's like a role model, and everything else is compared with respect to this, the best that can happen. So, and we know that some processes are more irreversible than others. So we can try to move toward making the processes more reversible. Okay. Another example here of reversible, irreversible processes. So on the left side, we do have a slow and therefore reversible process. Water is contained in a container. On the right side, there is a movable wall. So if we move the wall, this looks like a dam. If we move the wall very slowly from left to right, then the process can be considered as reversible, assuming that it does not cause sloshing, it does not create waves. So the process can be done back and forth without any trace on the environment. So as for instance, it pushes the plate to the right, work is done by the system, and then we can use the same amount of the work which has been done by the system. Now we can use this work and do this work on the system and push the plate back during the compression. So by expansion compression, work is generated by the system and then it's received back by the system. So it's a reversible process. Now if you let the process happen very fast, meaning that you let the movable plate to move very fast, fast expansion to the right, so what will happen is that some work will be done as a result of expansion. However, waves that also generate in the system due to sloshing, the waves go back and forth. Water has viscosity, friction, and some of the useful energy of like the gravitational energy will be converted to heat. Now if you let it expand rapidly and then you want to use the same amount of work which has been performed by the system on the surrounding, use the same amount of work, and you try to back, it will stop probably halfway. It doesn't come to the original state because some of the energy has been some of the original potential energy of water has been lost during this process. So B is a fast and therefore irreversible process. Unfortunately, I cannot answer any questions on online teaching, but please feel free to write comments under the videos right here on the course forum, email. So use all other sources of communication if you do have questions to ask. Okay, so some sources of irreversibilities are given in this slide. So friction, we already talked about friction as a major source of irreversibility. That's why in a piston cylinder, we usually assume a frictionless piston cylinder, because if there is friction, then we cannot simply go ahead and analyze the piston cylinder based on simple thermodynamic analysis. So while the expansion causes irreversibility, so we have talked about friction and wild expansion so far. Other sources of irreversibility, mixing of two fluids. If you mix two fluids, then how to separate them without leaving any effect on the environment. So mixing is irreversible process. Heat transfer across a finite temperature difference. So this is very important. Heat transfer, if there is a temperature difference, if there is a delta T, then heat transfer is irreversible. For instance, you put a can of soda in the ambient temperature, 20 degrees C. The temperature, the can temperature is 5 degrees C. So this heat transfer is irreversible. This is a very good example to understand it. So why this is irreversible, right? So it means that if you want to bring the temperature of the can back to 5 degrees C, you cannot just leave it on the, in the ambient condition. You would need to put it in the refrigerator. In the refrigerator, actually work has to be consumed by the compressor to reduce the temperature back to 5 degrees C. So this is a very good example. So without a refrigerator, you cannot cool down the soda can again. So heat transfer with a finite temperature difference, like from 20 degrees C to 5 degrees C. This is irreversible. And some other examples, electric resistance, it's irreversible. If electricity in the wire is converted to heat, then you cannot heat the wire to convert the heat to electricity again. Inelastic deformation of solids, if it's inelastic, it's non-linear. You deform like a polymer, a plastic, a metal. If for instance you compress a metal in the elastic range, it will come back because it's like the Hooke's law, linear law. But if you compress it so much so that it's deformed, like going to like the deformation phase, plastic deformation, it will not come back to the original state, so it's irreversible. And of course, chemical reactions are all irreversible because, let's say, as soon as you burn a fuel, you cannot just unburn the fuel, right? So it's irreversible process. All right, so now let's talk about another important concept, internally and externally reversible processes. So what does it mean? So when we are considering a system, the system itself has a boundary. So inside the boundary, that's the internal of the system. Outside the boundary, that's the external part of the system. So if a process is totally reversible, it involves no irreversibilities within the system and its surroundings. So that's totally reversible. However, sometimes it's easier and practical to consider internally reversible processes. So it means that a process is internally reversible if there is no irreversibility within the boundaries of the system during the process. So however, outside of the boundaries of the system, you may have irreversibility, but inside the boundary of the system, if there is no friction, there is no heat transfer with finite temperature difference, then it's internally reversible. Externally reversible only means inside the system there might be irreversibilities, but outside the system there will be no irreversibility, then that would be externally reversible. If it's totally reversible, means there will be no irreversibility inside and outside of the system. So let me give you a good example, which is the last slide of this part. Okay, So we want to look at a internally reversible process which has a lot of applications, and that's phase change. So on the left, so look at the left part. So you see that you do have a piston cylinder with the liquid in it. It's a phase change process. So part of it is liquid, part of it is vapor. So if we heat this system, and the system temperature is at 20 degrees C. So if we want to transfer heat, the temperature of the reservoir, the outside source, has to be higher than 20 degrees C. But if we want the system to be totally reversible, therefore the temperature of the source cannot be higher than 20 degrees C. Now the problem is that if the temperature is not higher than 20 degrees C, the outside temperature, there will be no heat transfer going on. So in order to have a heat transfer process, we keep the temperature at 20.000001. So there will be a very small heat transfer temperature difference in order to make the heat transfer possible, but at a very, very slow rate. So this way we do have heat transfer, but we have kept it very close to the reversible condition. So this means that externally now this process is reversible because the temperature difference between this reservoir and the system is negligible. Internally, you see that if the piston is frictionless and between the water and its vapor, because it's phase change process, there is no temperature difference. So water evaporates in this condition at 20 degrees C. It converts to vapor back and forth at the right, when the right pressure is applied here. So this is internally reversible as well. Internally reversible, externally reversible, therefore it's totally reversible. Now, if you look at the second part of this diagram, so here you do see the same system. So it is, the process is internally reversible no matter what, because it's a phase change. It's phase change frictionless, so it is internally reversible because the temperature of the water is the same as the temperature of vapor. Liquid water and vapor water have the same temperature, so it is internally reversible and it is frictionless, so there is no source of irreversibility in the system. Why we say that it's reversible? Because at 20 degrees C, the water vapor and liquid water can actually convert to one another at the same temperature. So it's a reversible process. So now if you look at it externally, you see that the outside temperature is 30 degrees C. Inside temperature of the system is 20. So there is a finite temperature difference. This finite temperature difference makes the external process irreversible. External process means outside the boundaries. This process is therefore irreversible. So this process that you see on the right side, part B, it is only internally reversible. It's still very useful because it's internally reversible and it helps us to analyze at least the internal of the system. Oftentimes it's important to be able to analyze the system itself, so internally reversible processes are extremely valuable. Okay, so this brings us to the end of this lecture. Thank you very much for your attention.